Hello everyone, you are welcome to part 2 of our electronics video tutorials. In the last lecture on part 1 of this class, we looked at the PN junction, which we said is called a diode. Now we started looking at the structure of the atom and then graduated gradually to the PN junction diode. We looked at the structure of the atom, we looked at energy levels, energy bands, and then we also came to the semiconductor material. We looked at partial conduction, the semiconductor material, and we also looked at doping, which is usually an artificial means of creating excess holes or electrons within the material. And then we looked at silicon being the most popular semiconductor material that is used. And then we formed a p-type material and an n-type material, and then putting them together also formed the PN junction, which we call the diode, PN junction diode. And this actually, if you look at the circuit as we have here, yes, this is the diode, the symbol of the diode, the circuit symbol of the diode. This side is the anode, this side the cathode. Like we concluded previously, the diode conducts in only one direction, which means that since this the anode is more positive and the cathode is more negative, if you apply positive here and a negative here, the diode conduct. But if you change the polarity, the diode will not conduct. So in that case, you can see that the diode conducts in only one direction. And in mechanical engineering, it could be likened to what we call the non-return valve. So in part 2 of our lectures, we are going to be looking at the application of the diode. And to be more specific, we are going to be starting with the application of the diode in power supply circuits, and we'll also look at the application of diode in caliper circuits. But the more popular application of the diode is in power supply, so we are going to look at that and then also progress from there. So in power supply, we have what we call half wave rectifier, and they also have full wave rectifier. So what we see here currently is a half wave rectifier, and I'm going to be explaining how this actually works. Now it is assumed that you guys have done something in electrical machines or applied electricity, and which means that by now you know how an AC is generated, an alternating current is generated. This is actually an alternating current. Now, if it were direct current, if it is this Vmax, if it were direct, once the voltage, let's say Vmax is 240, at every, and this is, let's say this is a timeline, this is a time axis. At every point in time, it will always be 240. So we have a straight line in DC. But in AC, it's not that way. It starts from 0, and as time goes, it rises to maximum, and then drops to 0, and then changes direction. And so it rises negatively, and then comes to 0 again, and then rises positively, comes to 0, and then continues. So this current is alternating between the positive and negative. That's why we call it the alternating current. Now there are certain appliances or devices that can use the AC directly as it is alternating. But also there are certain devices that you cannot apply AC to. They will get damaged immediately. Such devices will need direct current. If it is 240 volts, it must 240 volts always. It shouldn't be starting from 0, rising, dropping, changing direction. So the idea of rectification is to try as much as possible to convert this alternating nature of the current to a direct current. And that's what we are going to be using the diode for. We'll see how the diode can be used to achieve that. Well, of course, it may not solely depend on the diode, but the diode does the major work. So let's look at it. Here we say we are half wave rectifier. So let's see how it works and what we mean by half wave rectifier. Mind you that this is actually the waveform, alternating current, but what we want is a straight line. So we want to convert this one to a straight line. So how do we go about that? First of all, this is our circuit. This is a transformer. The AC input is here, and then we also have another AC output here. Since it's a transformer does not convert AC to DC. It just steps down or steps up the AC. So we have AC input here. The secondary of the transformer will also produce AC. But what we need is a DC. So in this case, this is our load. It could be the device or appliance that we want to supply the current to. So here in this case, we are using this diode in conjunction with the load like this, in series with the load. And then let's see what happens. Now, since the diode allows current to flow in only one direction, which means that if it sees positive here and negative here, it will conduct. But if it sees negative here and positive here, it will not conduct. So let's see what happens. During the for the AC, by the time the current moves from this point, goes to its peak, gets to 0, crosses and comes here, it would have completed what we call a full cycle. This is what we call a full wave. Then it starts again another full wave. So here we have 2 full waves, but usually it's continuous like that. So here, this is actually a full wave. But let's see what the diode here is going to be doing. So this is the positive half cycle. Here is positive half cycle, and this one is the negative half cycle. So when we apply current to the transformer, the output of the transformer is also AC. The current starts from 0 and rises to maximum and drops to 0. So let's see, from here to here, all this portion is positive and all this portion is negative. So any current that is applied to the diode, which is part of the positive half cycle, will go to the diode. So if we want to bring it at the terminals of the transformer, we can say that when this terminal of the transformer is positive, the other terminal is negative, and then it will change. By the time we go to a negative cycle, this time this side becomes negative and the bottom part becomes positive, and then it changes again. So it is alternating between the terminals. So when during the positive half cycle, that current that is fed here will apply a positive here and negative here. At the positive half cycle, this terminal is positive and that terminal is negative. So since we have positive here and negative here, the diode is going to conduct. So in other words, all the positive half cycles will go through the diode. Now when the current changes direction or it reverses and it goes into the negative, once it goes to the negative, it means that this time this terminal is negative and this terminal is positive. So once you have negative here and positive here, the diode will not conduct. So all this negative half cycle will not go to the diode. The load will not see any current. Everything will be off until the current now becomes positive again, starts rising. Then the diode will conduct again. In other words, this side has become positive again, and the bottom part is now negative. The diode will conduct again. Then when the current goes negative, the diode will not conduct. So at the end of the day, we are going to have only this positive cycle go through to the load. The negative cycle will not be seen, and the positive also goes through. So at the end of the day, you are going to see we have this 0, this 0, it continues like that. So only the positive half cycles get to the load. All the negative half cycles are cut off. Not cut off per se. They are not allowed to go through the diode. The diode does not conduct during the negative half cycle. So at the end of the day, we have only positive off, positive off, positive off. So what we have done is that we have only harnessed the positive half cycles of the AC. But that is not what we want. We actually want a DC. Here, already, all this portion means that the 0 point means that the load is off. There's no supply to the load. So if it's a device you are trying to supply, it takes positive and then goes off. It takes positive and it goes off. Even the positive is not steady. It rises from 0, it goes high, drops to 0, it goes off, rises high, 0 goes off, and continues that way. This is not very good. So which means that the half-wave rectifier does not really get us anywhere, but at least it gives us an idea of how the diode operates in an AC circuit. So from here we move on to another step where we have a full wave rectifier. The full wave rectifier, we have 2 types. We have the center tapped full wave rectifier, and we also have the bridge rectifier. So we'll look at them one by one. Now remember that in the previous one we're only able to harness the positive, and then during the negative it was off, positive, negative it was off. But how about if we now use two diodes, but we are not just connecting the two diodes, like connecting one diode here or connecting one diode here? It will not help us to achieve anything. So here you connect two diodes, and then you use the two diodes with a center tap transformer. Why is it necessary that the transformer must be center tapped? Center tap means that if you look at the secondary winding of the transformer, there is a tap in the center of the winding. So which means that if from here, from A to B is giving you, let's say, 24 volts, A to C will give you 12 volts, and then C to B will also give 12 volts. So if you add AC to CB, you get what AB is, which is 24 volts. So here the center tap helps you to get half the voltage at the output of the transformer, and then half also here. Then A and B will give you the full. So what is the essence of the center tap? Now once you create this center tap, it serves as a reference point to A and B, which means that C now becomes a reference point to A and B. In other words, C is always negative. Now the alternation will now be between A and B, which means that while C is always negative, there are times that A is positive. When A is positive, B is negative, and then it will change. A becomes negative and then B becomes positive. All this while C remains positive. So how does this help? So since we know that with the center tap, the center is always positive, the C, which is a reference, is always negative, we connect the negative of the load to C, so that we know that the negative is always seen there. Now we'll see how to direct all the positive to the positive terminal of the load. Now the idea here is that this load, which is supposed to be a DC load, which means that it does not like an alternating current, but it wants a direct one. Now in other words, you can say that this load always wants to see positive here and negative here. If you ever interchange it, it will spoil the load, it will damage it, or it will malfunction. So at the end of the day, what we want to achieve is that all the time there must be positive at this terminal of the load, and there must be negative here. But with the center tap transformer, already since the center is giving us the reference point, which is negative, it means that that side is always negative, so we don't have a problem. So we connect the negative to the negative terminal of the load. Now all that we are left to achieve is to ensure that the positive terminal of the load also always sees positive. How do we allow only positive to arrive at the positive terminal of the load while this is always negative? So let's see what happens. Now we have D1 and we have D2. Now between these two, as you can see, D1 is connected to terminal A of the transformer, and then D2 is connected to terminal B of the transformer, and all of them, D1 and D2, they all end up at the positive terminal of the load. So at the end of the day, since this side is always negative, all we need is to ensure that this side is always positive. So what happens in this connection? Now when A is positive and B is negative, you realize that since when A is positive, D1 is forward bias, and when at that time B is negative, and then diode 2 is negative, reverse bias. So under that condition, when A is positive and B is negative, diode 1 will conduct, and then the first positive half cycle will go through diode 1 and arrive here. So the load is seeing positive here, whilst this is always negative, it's seeing positive. Now let's see what happens when the AC alternates, and this side becomes negative, this side becomes positive. Will the load still see positive here in spite of the alternating nature of the terminals of the transformer here? Okay, so now let's alternate. Now this time A becomes negative and B becomes positive. The moment A becomes negative, diode 1 cannot conduct again because it becomes reverse biased. But when A is negative, B is positive. Once B becomes positive, diode 2 becomes forward biased and it conducts. So at the end of the day, the D2 will now conduct the positive here. So whether it is A that is positive or it is B that is positive, all the time, whether it's A or B that is positive, the positive waveform always ends up at the positive here. So you realize that for this half cycle where A is positive, D1 conducts, and when it changes and B becomes positive, D2 conducts, and then when it changes and A becomes positive, D1 conducts, and they continue like that. So by using these two diodes with the center tap transformer, we always ensure that, unlike the halfway where it's only one diode, so it conducts and then nothing happens, it goes off, it conducts again. Using the two diodes with a center tap, the positive conducts and the positive. So at the end of the day, the load is positive here all the time and then negative here all the time, irrespective of how alternating the input is. So with this, we have realized that we have actually harnessed all the full wave. Unlike here where we have only half wave and it goes off for the negative half cycle, another half here we have all the wave, full of the wave as positive. So by so doing, so we can say here that we have been able to harness only the positives from the output of the transformer. At least we are getting somewhere. This is better than the half wave. So because here it actually goes off, positive goes up, but here it doesn't go up at all. It's only positive. So the load sees positive here all the time and negative here all the time. But then it's not the best, because what we want is actually a straight line. But what we have here is rising from 0 to high, dropping to 0 and rising again. So it is not very smooth, it's not a straight line. But at least by using the diode this way, we've been able to achieve something to make sure that the load is always seeing positive here, negative here. So we'll come back to here, we'll come back to this and see how we can improve upon it. But before that, we have to also look at how the bridge rectifier works. The bridge rectifier actually helps to also produce an output waveform like this to the load. But how does it work? So here we don't have a center tap, but instead of using a center tap and two diodes, we have just a normal transformer with 4 diodes, where these diodes are not labeled. So I'll point to them as when I'm talking about the operation. So let's see what happens here. Since there's no center tap, it means that when this side is positive, this side is negative. Then it alternates. This side becomes negative, and this side becomes positive. So let's see what happens. Bear in mind that this is the ground, which is also known as negative. So as far as the load is concerned, you want to see negative here all the time and positive here all the time, irrespective of the alternation that is taking place here. So let's see what happens. When the top is positive and the bottom is negative, you realize that when the positive gets here, it forward biases this, but this one will be reverse biased. So it means that this diode here will conduct the positive to the load. So the load sees positive here. At the same time, since this side is negative, when the negative gets here, this one is reverse bias, this one is positive forward bias, because as you can see the orientation of the diode, it makes it forward bias, and then the negative arrives at the ground. So at the end of the day, this allows the positive to reach here, and this one allows the negative to reach the ground. Now this symbol here tells you that it is the ground. It means that they are all interconnected. Just that you don't want to draw a line here and then cross it all around, but this shows that they are all at the same potential. You might as well remove the small lines there and then project this one down and then join all of them. So it tells you that they are all interconnected and they are at the same potential. So in this case, we have seen that when the top is positive and the bottom is negative, this diode conducts the positive to the terminal of the load, positive here, and then this diode allows the negative to arrive at the ground here. So for the first half cycle, we have positive here and negative here. Let's see what happens when it alternates. Now the top becomes, let's say the top has become negative, the bottom is positive. When the top becomes negative and it gets here, because it's negative, this one will be reverse biased and this one will be forward biased. So the negative will then again be conducted by this diode to ground again. So for the next half cycle, we will see that the load is still seeing the negative here. When this side is at the time that this is negative, this side has now become positive. So let's see what happens. When the positive half cycle gets here, this one becomes reverse biased and this one becomes forward biased. So the positive goes through this diode and arrives here. So at the end of the day, we are seeing that for both alternations, when this is positive and negative, this one conducts the positive here and this conducts the negative to ground. And when this side is negative and this is positive, this conducts the positive here, and then this one conducts the negative ground. So realize that for all the cycles of the input, you realize that the load is seeing only positive here and seeing negative here. At the end of the day, we have harnessed all the positive to here, and then we have the negative potential here. So the load sees positive here all the time, negative here, just like in this case. But like I said, you realize that I did not talk about the capacitor that is here, because that is actually there to help improve the waveform, and that's what I'm going to be talking about next. So these two will give you the same output waveform. All the positives will arrive at the load, and the negative here. So the load will see all this positive, but like I said, it is not smooth. What we need is a straight line. So how do we get this to become close to a straight line or a straight line? So that is the purpose of the capacitor you are seeing here. The capacitor here is performing what we call smoothing. In other words, it is helping to smoothing the waveform, because we need a straight line, but this waveform is just rising, falling, rising, falling, rising, falling, but we need a straight line. So what happens when you introduce a capacitor in parallel with the load? This is exactly what happens. Now remember that this is the kind of waveform with both the center tap wave rectifier and the bridge rectifier. This is a waveform they end up giving to the load, but the load needs a steady one. So what we need to do is to prevent this current from falling to zero. If it can stay at whatever level it is throughout time, that's what we want. But here it rises and then falls, rises and falls, rises and falls. So how can we get this one to how can we prevent it from falling? So the capacitor here, I believe in your applied electricity, you have been told that a capacitor basically stores electrical charges. It stores electricity in the form of electrical charges. So what happens is that when this current rises from 0 to maximum, as it gets to maximum, it charges the capacitor. Now when it charges the capacitor and then it's beginning to drop, since the capacitor is fully charged and the current that is supplied from the rectifier is beginning to drop and the capacitor is fully charged, the load, instead of depending on the current from the rectifier, it will now start drawing current from the capacitor. So at the end of the day, though this one rose, the current rose to maximum, is beginning to drop now, though that one is dropping to zero, the load is not going to see the one that is dropping to zero, because it is now taken from the capacitor that is fully charged. So capacitor, as current rises, capacitor gets fully charged. As current is dropping, then the capacitor will now serve as a source of supply to the load. So it begins to discharge the current that the charges that it has stored in the form of electric current. It begins to discharge it to the load. So now from here, the load does not take from the rectifier again, it begins to take from the capacitor. So the capacitor now begins to discharge gradually. The discharge of the capacitor will usually not drop just like the way the one from the rectifier drop. So it will take a longer time for it to drop to zero. So unlike the output from the rectifier, which draws from zero within a short time, this one will take quite some time before it drops to zero. So let's say when the capacitor is fully charged, it will take this full length here in order to drop to zero. So when the current rises, charges the capacitor, and is beginning to drop, the load takes from the capacitor begins to discharge until it can go to zero. But guess what is going to happen? By the time the capacitor is discharging, the load is drawing from the capacitor and is going down, is dropping, and it gets here. By the time it gets here, the current from the rectifier would have gone down and will rise again. So as the capacitor discharges and it gets here, it was supposed to go down. But by the time it gets here, the current from the rectifier would have gone to zero and then will rise again, and then it will take over the supply and start supplying the load again. and at the same time charging the capacitor. So when the capacitor gets charged again and the current is dropping to 0, the capacitor begins to discharge again. By the time it reaches here, the current from the rectifier would have dropped to 0 and rising again. It charges the capacitor and then supplies the load, and then the capacitor gets charged again. As it's going down, the capacitor begins to discharge to the load, and it continues like that. So at the end of the day, by the introduction of a capacitor, we have the current rising from 0 to maximum, and beginning as it gets to maximum, it starts going this way. Instead of going to 0, it goes this way, rises again, it goes this way, goes this way, rises again, goes this way, and it rises again. So at the end of the day, the load does not see current going to 0, because as the current from the rectifier is dropping to 0, the capacitor discharges to the load. So the load does not see the current go to 0. So at the end of the day, the waveform that we are going to see by using the capacitor here will be something like this. Instead of this that we saw initially, now the current will be like this. It never goes to 0. At least we can see that this waveform is closer to a straight line than this particular one. So by so doing, by the introduction of the capacitor, we have smoothened the waveform. So the function of the capacitor here is to perform what we call smoothing. Now, assuming I told you that the capacitor, let's say the capacitor will discharge, if it were left alone, it will take this time to discharge. What if the capacitor is such that it will take even a longer time to discharge? Let's say it will go gradually. It will take a long time to discharge. It means that by the time it is getting here, that's when the current from the rectifier comes and charges it again, and charges it again, and then so at the end of the day, you are not even going to have it drop down a little. It will almost be like a straight line. By so doing, we have fully rectified the AC waveform into a DC. So a bigger capacitor will give out a smoother waveform, and this is what we want. And yeah. So but usually after smoothing, we are going to have, it's usually not perfect. You are not going to have a pure DC. It is only batteries that produce pure DC. But so long as you are using a rectifier, after rectifying it, you will not get a pure DC. In other words, you will never get a straight line. There will be some small ripples of AC on it. And even with that, you can use another type of capacitor, usually the ceramic types, to filter out the AC, so that it can be smoother than usual. By the end of the day, it will still help the device to work, the device which needs DC to work properly. And so that is it with the full wave rectifier. But then we have polyphase full wave rectifiers. Now these ones without using the capacitor already provides what I would say a smoother waveform as compared to the normal full wave rectifier. Here with polyphase, we have 3-phase or 6-phase, as you can see here. Now when this terminal is positive, these other two are negative. When this one becomes positive, the 2 becomes negative, and when this one becomes positive, the 2 becomes negative. So the positive is changing from terminal to terminal. Positive, and whenever one is positive, the other 2 are negative. So you can see that already with this one is what we call 3-phase. Here it is a single phase. So you have just one current flowing, rising, dropping, changing direction and going. But with the 3-phase, we have each of the terminal produces this current, alternating current. So at the end of the day, you are going to have 3 currents. As this one is producing its alternate current, this is also producing its alternate current, this is also producing its alternate current. But they produce at 120 degrees phase difference. This one will cover 120 degrees before the next one also comes, and then it continues that way. So let's look at this. Already with the behavior of the the 3-phase, you can see that this phase 1, phase 2, phase 3. Okay, So when phase 1 is supplying to the load, it rises and then it drops in this phase 1, and then this phase 2 also, and this phase 3. But see what happens when phase 1 rises and is dropping. By the time it's dropping, it doesn't get to 0, and then phase 2 takes over, and then phase 2 also rises and begins to drop. It doesn't get to 0, and then phase 3 takes over. Phase 3 begins to rise and it begins to drop. It doesn't get to 0 in phase 1, it begins again, and it continues that way. So you can see that already, without even the diodes, without even, how do you call it, the capacitor, with the 3-phase, the current never gets to 0. The load does not see the current dropping to 0 in the first place. So you can imagine what happens when you now apply, how do you call it, a capacitor to it. So now the capacitor, when this rises to high, it charges the capacitor, and it's dropping, the capacitor begins to discharge. It begins to discharge, and then phase 2 takes over, charges it again. As phase 2 is going down, the capacitor begins to discharge, and then as it's going down, phase 3 takes over, it charges it again, and as phase 3 is dropping, the capacitor begins to discharge, and then phase 1 begins and it continues. So at the end of the day, once you introduce a capacitor, it even produces a smoother, much smoother output waveform. As you can see here, it rises and then it doesn't even go down. Okay, this one is for the 6-phase. So once you introduce a capacitor, you realize that it becomes smoother straight away. And then even if it's 6-phase, that one, if without the capacitor, has already produced a smoother waveform. As you can see it, this is phase 1, phase 2, phase 3, phase 4, phase 5, phase 6 of them. By the time this one, the phase angle between these ones is smaller. So unlike this one where it has to go way down before this one takes place, this one doesn't go way down. As phase 1 rises and is beginning to go down, phase 2 takes over. It charges, and then as it takes over, supplies, as it begins to go, it doesn't reach anywhere. Phase 3 takes over, phase 4 takes over, phase 5 takes over, phase 6 takes over, and then it starts again. So at the end of the day, the load is not going to see any current going to 0 or going below this. So this one is even smoother. So by the time you apply a capacitor to it, it's almost like a straight line. So the polyphase full wave rectifiers give smoother output waveforms than the single phase. I believe we've learned much. So we move on from here to what we call the clipper circuits. Now, this is also another application of the diode in the clipper circuits. So let's see how the clipper circuit works. First of all, we know that the diode actually, when it's conducting, it develops about 0.7 volts or 0.6 volts for silicon across it, which means that the voltage that is applied across the diode must be greater than 0.6 or 0.7 before it can conduct. If the voltage is below 0.6, the diode will not conduct. So the question is, how does that help, or what does that help us to achieve in this circuit? So let's look at this. First of all, when we this is the input waveform, which means that this is a waveform that is applied to this. Okay. So first of all, let's see what happens when this voltage is rising from 0, and it is rising. Now, until it is above, okay, let's use 0.7 as a standard. Excuse me. Let's use the 0.7 as the 0.7 as a standard. So here we would see that when the current is rising from rising from 0, since it is not above 0.7, the diode is not conducting, so all will go to the load. So from 0. whatever to 6.9, let's say 6.9, the diode is not conducting because the voltage is not beyond 0.7 or even up to 0.7. The diode is not conducting. So from 0 to 0.7, all will be conducted across, all will be sent to the load. But the moment the voltage goes beyond 0.7, this diode becomes begins to conduct, and then it serves as a short circuit. The moment, because the forward resistance of a diode is very small, it's negligible. So the moment the diode begins to conduct, the moment the voltage rises above 0.7, the diode begins to conduct. It becomes like a short circuit. It's just like a wire. You've connected the wire across the load, and once that happens, all the current, instead of going to the load, now begins to go through the diode. So any voltage above 0.7 will not be no current will flow. Once the voltage goes beyond 0.7, no current will flow to the load. So it means that any voltage above 0.7 has been clipped. When it now begins to drop, so from 0 to 0.7, it goes to the load. The moment it goes above 0.7, the diode conducts and the load does not see anything. And then until it goes and then comes back again, the moment it goes below 0, the diode does not conduct again and the load begins to see it. And then when it changes direction, remember this, the input waveform is alternating. The moment it changes direction, it becomes negative. This side becomes negative. The diode does not conduct at all throughout, whether it's rising or dropping. So long as it's negative, the diode is reverse biased. So the diode does not conduct. And if the diode does not conduct, it means that current will be sent to the load. So for the negative half cycle, all goes straight to the load. So at the end of the day, you are going to have a waveform like this. So from here to here is from 0 to 0.7. The moment it begins to go above 0.7, the diode begins to conduct. The diode begins to conduct. So once the diode is conducting, it short circuits the load and no current flows to the load. So from anything above 0.7 does not go to the load, because it causes all the diode conducts and it causes all the current to flow through the diode. So all these things does not go to the load until the current goes below 0.7 again, and then the diode does not conduct, and then the load begins to see the current again. So the load does not begins to see the current again, and then it changes direction. When it changes direction, this side becomes negative and this is positive. The diode becomes reverse biased. So for the negative half cycle, the diode does not conduct again, and all the negative half cycle goes through the load until it becomes positive again, even positive. So long as it's below 0.7, the diode does not conduct and the load will see it. But the moment it goes beyond 0.7, the diode begins to conduct and then the load does not see anything, and it continues that way. So at the end of the day, by using the diode this way, it clips any voltage above 0.7 positive. So this is what we call the positive shunt clipper. Shunt or parallel. It means that the diode is connected in parallel to the load, and it helps to clip the positive half cycles. Now, in reverse, if you change the direction of the diode like this, the terminals of the diode like this, it will perform a similar action but in opposite way. In this case, it will clip only the negative half cycles, and then it will allow only full positive half cycles to go through for the negative shunt clipper. Okay, so yeah, so we'll continue from here, and then now in this circuit you can see that we are dealing with 0.7 because that is a forward voltage across the diode. But question is 0.7 is very small. In most circuits work with voltages beyond 0.7. So what happens when you need a greater voltage to clip? Because here you can see that it clips any voltage that is above. If it's a positive clipper, it clips any voltage that's above 0.7. So first of all, it can tell you that this can be used for protection in a circuit. So maybe the device you are supplying, the load you are supplying, does not need a voltage beyond 0.7. So you use this to make sure that it does not go, the voltage doesn't go beyond 0.7 to protect it. But like I said, most devices will need more than 0.7. So in that case, what do we do? Hold on, let me check something. Okay. Okay, so let's go back 1 minute. let me be sure of something. Okay, so now like I said, usually most devices will need more than 0.7 voltage to work with. So how do we help to clip greater voltages? So we introduce what we call a bias voltage into the circuit. As you can see here, this is for the positive clipper. Now we put a bias voltage here. Now what happens if, assuming we want to clip the device that we are working with needs to operate with let's say 3.7 volts. Let's say it needs to operate with 3.7 volts. Any voltage beyond 3.7 should be clipped, should be cut off. Should be cut off. It doesn't go to the load to destroy it. So what we do is that, since when the diode is conducting, it develops 0.7 volts across it. In order to achieve the positive clipper, the bias clipper, we introduce a bias voltage of 3 volts in series with the diode. So what happens is that anytime the diode is conducting, the total voltage across it will be 3.7. And then so at that point, the load does not see anything. Any voltage above 3.7 will go through this branch, and then current will not go through the load. So by introducing the bias voltage here, you raise the operating voltage of the diode here to a greater one. So if you introduce 3 volts here, it means that the conduction, the voltage developed here will now be 3.7. So which means that when the voltage goes beyond 3.7, the current will now start flowing through this arm, and it will prevent current from going to the load to damage it. So by so doing, we'll lift the voltage, we increase the level of voltage that can be clipped. Once you understand this, the bias negative is always the other way around. And I believe you can have books, and then you can go on the internet to read more about the clipper circuit, but it's pretty straightforward. Okay, next we also go into another application of the diode in what we call voltage regulation. Others will say voltage stabilization, voltage regulation, or voltage stabilization. Okay, so what is this about? Now you understand that we said that whenever the diode is conducting, it develops 0.7 volts across it. So let's say that you have a load. If you have a load that operates with 0.7, see what is going to happen. Now this here is a variable source, which means that it can vary from 0 to a particular level of voltage. And then this is a resistor, a limiting resistor. Now what happens is that when this voltage is varied, usually the voltage, since this and the series resistor here, or the limiting resistor here, the resistor is in series with the diode here, it means that the voltage drop across the diode plus the voltage drop across the resistor here should give us a total voltage here. But since this one, the diode will always have 0.7 across it, even when you are varying the voltage from the source here, the changes will only be seen in the voltage drop here, because this is always 0.7. So let's assume that the voltage currently that you have set here is, let's say, 2 volts. So if the voltage is 2 volts, this one will always have 0.7 across it. So which means that 1.3 volts will be seen across here. Now, assuming you increase from 3 volts to, let's say, 10 volts, this will still be 0.7 volts, and then the remaining voltage will drop across here, which will be 9.3 volts. So you realize that by using the diode in this way, even though the input voltage is varying, there's a constant voltage across the diode. So if you want to supply a load or a device that needs 0.7 constant voltage, it doesn't need fluctuation, you connect it in parallel with the diode like this, it will ensure that even though there's variations in the source, the diode will also, the load will also have a constant voltage. But then again, just like I said in the clipper circuit, most loads will require more than 0.7 volts to operate. So let's say our the load requires about 7 volts to operate. 7 volts. So in this case, since it's 7 volts you want, it means you have to connect about 10 of these diodes in series in order to get 7 volts. Each of them will drop 0.7, 0.7, 0.7, 0.7, 0.7, 0.7. 10 of them will give you 7 volts. Yes, it will also give you a constant 7 volts across your load. So question is, what about if you need about 70 volts? It means that you need about 100 diodes in series, and that will make your circuit very bulky. So the developers the designers of the diode thought that, okay, why don't we since it will require more diodes in order to get greater constant voltage, and we know that usually when a diode is reverse biased, the reverse voltage, you can increase your voltage and increase it. Before it can break down, you have to increase the voltage to a very high level, which means that in the reverse, a diode can actually have a bigger voltage developed across it until breakdown. So they intentionally designed a diode that will only operate in the reverse direction, and with that one, it can, because it's in the reverse direction, it can operate with a higher voltage, though it's a single diode, and that diode is what we call the Zener diode. The Zener diode. This is a symbol of the Zener diode. The Zener diode operates in the reverse direction. So when it's reverse biased, that is when it does its operation. So with this, for example, you can see that this is a 12.6 volts Zener diode. The Zener diode will always have the constant voltage across it. So once you connect your load across the Zener diode, you can be certain that the load will also have that constant voltage across it. In other words, you are regulating the voltage, you are stabilizing the voltage. The remaining voltage will be dropped by this resistor here. Are we okay? Okay. There was something I was supposed to tell you here. I didn't tell you the function of this resistor here. Now, the function of this resistor here, like I mentioned here, is also serving as a current limiter. A current limiter. What's the function? Assuming these were not there, and then what happens is that, assuming these were not there, once the diode, let me use this one. Assuming these were not there, this resistor were not there, once the voltage goes beyond 0.7 and the diode begins to conduct, remember that when the diode begins to conduct, it acts like a short circuit across the load. But when this resistor is not there and the diode short circuits it also short circuits the power supply. And once there's a short circuit of the power supply, there could be maximum current flowing. There could be a blast. It could cause fire. So we don't want that to happen. You will never want to short circuit the power supply, especially when the voltage is high. There's going to be trouble. So this is there to prevent the source from being short circuited. Okay, but this one is not performing a similar function of preventing short circuit, but it helping to develop the rest of the voltage that is coming from the source, because this diode will only allow a constant voltage across it. So where would the rest of the voltage applied there go? It will be developed across it. Okay, so from here we move on to another topic, and here we look at the transistor. Now the transistor is just like a diode, but instead of having a P type material and an N type material, put them together, you can either have 3 materials, P, N, another P material, or it could be N material, P material, and then another N material. So this is the schematic symbol of the transistor. It's 3-legged. The 3-legged, one is collector, one is base, and then one is emitter. So whether it's a PNP or NPN, you will always have the collector, base, and the emitter. And if you look at it carefully, you realize that the collector, the material there is bigger as compared to the emitter. The emitter is smaller, and the base is the smallest of all. The base is the smallest of all, and usually because for the proper operation of the transistor, the base is usually thin. It's lightly doped. So if it is the base is N-type, it means that the electrons there are very few. If the base is P-type, that means the holes there are very few, and that the design is intentional for a purpose. As the name implies, this is a collector. It is meant to collect more, so it usually has to be big. So let's go straight to the point and see how the transistor operates. We look at the transistor action. So here we look at an NPN transistor. Now, once you understand one, the other one is easy to go. So we use the NPN transistor for our discussion here. Now, as you can see, it looks like two diodes. This form one diode, and then this and this also form another diode. So it looks as though two diodes joined together, but the function here is quite different. So for the proper operation of the transistor, like I said, the base junction, the base material is usually lightly doped. It has very few, few, if it's a NPN, few holes here. And then for proper operation also, the emitter and then the base junction, this is the emitter, this is the base junction, should always be forward biased, and then the base and collector junction should be reverse biased for proper operation. How does this work? So first of all, you can see that this is an N-type material, this is a P-type material. So positive terminal of the source is connected, the voltage source is connected to the P-type, and the negative is connected to the N-type. So at the end of the day, the negative terminal is going to propel or push electrons from the N material into the base, while the positive attracts the holes from the base. But you see, since the since the base is lightly doped, there are very few holes here. So most of the electrons that are pushed from the N-type material here, they only have few few holes to occupy, and then the rest of them will be pushed here. See what is happening when this side is forward biased. This side, when the NP junction is forward biased, the emitter base junction is forward biased, the base collector junction is reverse biased. And see what happens here. You can see that this is positive terminal connected to the N type, which is negative. So the positive will attract the electrons from here, and then this is negative. The negative will also attract the holes from here. So anyway, this one is reverse bias, but it's reverse bias, but to this voltage source has reverse bias this junction, but has also forward bias this. So what is happening is that the electrons that were propelled here, few of them will fill the holes here, and the rest of them will jump here. And the reason why they will jump here is because this, as you can see, the source here is bigger than the source here. Once you see the battery sign here, this is one battery, these are two batteries. This tells you that the voltage here is greater than the voltage here. So this one has a greater force of attraction to the electrons as compared to this. So though this positive here will attract some of the electrons to the base, majority of electrons will be attracted towards the collector. So at the end of the day, we are going to have very small current flowing through the base and a huge amount of current flowing through the collector. The electrons that couldn't combine with a few holes here, all will join the electrons here and come out of the collector, having a bigger amount of electrons flowing. So this is basically the transistor action. This is for NPN transistor. Once you understand this, the PNP becomes easy. So for your own good, use the explanation I've given here to also analyze this one and get your conclusion. Anyway, there's a write-up here that you can use. But if I were you, I wouldn't read the write-up first. I'll try to analyze it by myself and then to see if I have understood it before I read. So if you do your analysis and you read and it tallies with what your analysis came out with, then you know you're on the right track. Okay, so this is telling us, this is a Kirchhoff's current law, telling you that the emitter the emitter current is usually the combination or the addition of the base current and the collector current. The two of them come together to give you the emitter current. So whichever way, whether it's NPN or PNP, you know how it's going to be. So as you can see here, this NPN, collector goes, base current goes, and then comes out from the emitter. And then for PNP, we also have the emitter having split into the collector and then the base. Now you have to understand that this is looking at how do you call it, original or current flow direction, not conventional. We have conventional flow of current, and then we have real flow of current, the real direction of the current as it flows. Okay, and I'm sure all this will be explained to you in your applied electricity. So now, okay, this is another illustration of what we've already said. Another illustration here, they are using the circuit symbol. So this one, it tells you how to use the circuit symbol instead of using this in a diagram. In a circuit, you don't usually use this. You use the circuit symbol, and this is the way you present it in a circuit. Okay, so to round up this part of our lectures in electronics, we are going to start with the introduction to amplifiers, which means that we are looking at how the transistor can be used as an amplifier. Already, the transistor action has given us an idea of amplification, because we have electrons here, holes here, electrons here, and since this is forward bias and this reverse bias, the electrons here are pushed to fill holes here, and because the holes here are small, few, only few of the electrons fill the holes here, and the remaining are pushed here and attracted by this one to come out of the collector. So at the end of the day, we are going to have a huge amount of current flowing out of the collector, and that gives us an idea of amplification. So now we have the transistor being used for amplification. Now, the transistor on its own may not function optimally, though it can do the amplification, but it will not give you optimum results, in that there could be a lot of noise and interference and unwanted signals inside, which is actually noise. So let's look at the amplifier as a black box. So usually if the transistor is the main amplifier, but there are some other things that needs to support the work of the amplifier to help it operate optimally. So in this case, if you consider the amplifier as a black box, it has an input, an output, and has a power supply. Every amplifier has an input, an output, and a power supply. The power supply is what helps the operation of the transistor, which is what we'll be looking at when we get here. And we also have the input signal. So assuming it is let's say an audio amplifier, it means that the input will be an audio input, and then to give us a louder output, and then making use of the power supply to it. So let's look into the black box. In the black box, this is the active device, which is our amplifier. Let's say the transistor. As you can see, it has 3 legs. 1, 2, 3. Input, output, and then power supply. Okay. So here, what are all these things doing here? We have the bias generator, another bias generator, DC power supply, positive and negative. We have DC block, which is the capacitor here. They are performing what we call DC block. And we also have the coil here, or inductor. They are performing AC block. What are they all there for? So first of all, the power supplies are actually what gives power to the active device, the transistor, to operate. But then you know that you don't just apply power to it. The transistor has to be properly biased. Like we said, the emitter base junction has to be forward biased, and then base collector junction has to be reverse biased for an NPN transistor. So in this case, though power supply is applied to the transistor, we have to make sure that proper biasing is done. So the proper biasing is achieved by using these bias generators. These bias generators helps to ensure that proper biasing of transistor is achieved. Then after biasing, now most of the time the power supply to the transistor is not pure DC. It could be an AC that has been rectified to DC. And you know that whenever you rectify AC to DC, it is never pure. You get close to a straight line. Even if it looks like a straight line, it's never straight. There are still some AC ripples inside, AC components inside. And you don't want that one to get into the amplifier. Because usually if it's an audio amplifier, the audio that is coming also is alternating in nature. It's like AC, just that it has varying frequency, but it's also alternating in nature. So if in your power supply it is rectified, and since rectified power supply that is not pure DC, and there are going to be AC components, you don't want those AC components to interfere with your input. So you use what they call AC block. Now the inductors, the coils here prevents the flow of AC through them. So by the application of the coils here in this way, it blocks any AC ripples that may be may be in the power supply to our amplifier. Another way of saying that, it filters out any AC component in the power supply so that we can be sure that very close to pure DC gets to our amplifier to properly bias it. Then once we have now dealt with any AC ripple in our power supply and the amplifier is the transistor is properly biased, then we now feed in our input. But as you can see, the input is not fed directly to the amplifier, the transistor. There's also what we call DC block. Another DC block here. What is all this about? Okay. Now, like I said, if it's an audio amplifier, the audio is AC in nature. But you realize that maybe the AC, maybe let's say it's an MP3, okay, let's say a DVD player. You are playing DVD. I'm using DVD because I want to let you know why we need to block some DC. Or okay, any MP3 player, whatever it is producing the audio that you want to amplify. Bear in mind that whatever is producing the audio is a circuit on its own. So which means that it also has a power supply to it, which is DC. And then it is ultimately DC. And what you want to amplify is your audio, which is AC. It is alternating in nature. You want to amplify it. So there's a tendency that because the circuit producing the audio has DC supply to it, there's a possibility that there may be some DC components in your audio which you don't want to be amplified. As for the amplifier, whatever you feed in, it will amplify it. So when the DC which is maybe polluting your audio signal gets to the amplifier without being blocked or filtered out, the amplifier will amplify everything. You hear the sound, but there's going to be some noise inside. So the capacitor here is here to filter out any DC component or block any DC component that may be in your audio signal. So at the end of the day, once the DC is blocked, then you have only the audio getting here to be amplified. And there's another one at the R2 stage. Just in case this does not the first DC block, the capacitor does not do a very good job, and some of the DC components end up being amplified together with your audio, then this one will also do the final work by blocking them so that your loudspeakers will not have noise in them. You can hear your audio clearly. So this brings us to the end of part 2 of our video tutorials in electronics 1. Part 3 is not actually going to be part 3 like something I'm going to do now. I've already done it. In fact, when the lockdown started and we were supposed to do our online lectures, by then we had done some lectures in class. So I did a video tutorial starting from where we stopped, so which is what you are going to see as your part 3. But to some people, that was the first video they ever had for their classes. So when you listen to it, it may not look like a proper continuation of what we have done, but at least it will flow. So watch out for part 3. Thank you very much for your time. God bless you.